Hi guys, welcome to this video on 45, 45, 90 degree triangles. So 45, 45, 90 degree triangles, we're going to be learning to use the ratios of a 45, 45, 90 degree triangle to calculate missing sides. We're doing this because 45, 45, 90 degree triangles are important tools of design and construction. And then you're going to be able to find a leg or a hypotenuse of a 45, 45, 90 degree triangle given 2 out of 3 or 1 out of 3 sides. So, what is a 45, 45, 90 degree triangle? A 45 degree, 90 degree triangle is an isosceles right triangle. Both of its legs are congruent, and the hypotenuse is a differentiated third measure. So, if I know that a 45, 45, 90 degree triangle has two sides, then the two legs, I can find the measurement of the hypotenuse using the special ratio. Similarly, if I have the hypotenuse, I can calculate the measure of the legs. And it's important to know that any isosceles right triangle is going to be a 45, 45 degree triangle. 45, 45, 90 degree triangle, no matter what. So, what makes it so unique? Every 45, 45, 90 triangle has a unique ratio between its legs and hypotenuse. That is, I can multiply the measure of the legs by the ratio to calculate the measure of the hypotenuse. Or I can divide the measure of the hypotenuse by the ratio to calculate the legs. The ratio that exists between the legs and the hypotenuse of a 45, 45, 90 degree triangle is square root of 2, or approximately 1.414. So, be careful. When I say multiply by the square root of 2, remember that you cannot really multiply a rational number by an irrational number. So all you can do is evaluate and simplify it. Example, 5 times the square root of 2 is 5 times the square root of 2, not the square root of 10. You cannot combine them in any way, shape, or form. If you are dividing by the square root of 2, you must simplify your answer as much as possible. And this includes rationalizing the denominator if it is necessary. Because remember that you cannot have a radical number in the denominator. So, in this example, what are the missing sides TV and SV in the triangle below? So, it is marked that ST and TV are congruent. This means we have an isosceles right triangle because of the right angle here. So, with the markings and knowing this is a 45, 45, 90 degree triangle, TV must be congruent to the already given SV and must measure 6. To calculate the measure of SV, or TV must be congruent to ST. Oh, pardon the mistake on my part. TV must be congruent to ST, and that's equal to 6. SV must be equal to 6 times the square root of 2. Since I am going from the leg to the hypotenuse, I'm going to multiply the measure of the leg times the special ratio square root of 2, and since 6 is real and rational, and 2 is irrational, I cannot actually multiply them. My final answer is simply 6 times the square root of 2 for the hypotenuse. In this example, what are the missing sides in the triangle below? I know that this is an isosceles, so two congruent sides, right triangle, and the hypotenuse is given to me as 26. So I'm going to try to find E, because F must be congruent to E. It's marked as such, and I know that this is a 45, 45, 90 degree triangle, so that means that those sides must be congruent. So, in order to calculate the measure of F, I'm going to take the hypotenuse, 26, and I'm going to divide by the square root of 2. So, I can't leave it like this. I must rationalize the denominator. So I'm going to multiply by square root of 2 over square root of 2. And on the top of my fraction, I'm going to get that F equals 26 times the square root of 2. And on the bottom, the square root of 2 multiplied by the square root of 2 is 2. So now I can divide 26 by 2 to get that F is equal to 13 times the square root of 2. And then since I can use this fact up here, F must be congruent to E. b must also be equal to 13 times the square root of 2. So, real world example here. On a baseball diamond, each of the base paths is 90 feet. So I'm going to mark that as such, 90 feet and 90 feet. When a runner attempts to steal second base, the catcher tries to throw him out. How many feet must the catcher throw the ball in order to throw the runner out? So basically, I am trying to calculate the distance between the two and calculate from here all the way to up here. So if I am calculating this missing measurement, I know I have two congruent sides in this triangle, so it's isosceles. And what's helpful to know is that all of the sides, or all of the base paths in baseball, form 90-degree angles with each other. So I have an isosceles right triangle. So it is helpful to know that a baseball diamond, has 90-degree angles between paths. So that creates a 45, 90-degree triangle. So, using that fact, I can then say that the distance, so the distance that the catcher has to throw the ball must be equal to 90 times the square root of 2 feet, using the properties of a 45, 45, 90-degree triangle. And if I were to approximate that, it would be approximately 126.76, or 26, excuse me, 126. I made a mistake with my math. I apologize, guys. Let me fix that. 127.26 feet. I apologize. My math was a little off there. So it's approximately 127.26 feet. However, 90 times the square root of 2 feet is the official answer that we can give for a distance between home plate and second base. So, in summary, 45, 45, 90 triangles are isosceles triangles. Specifically, they are isosceles right triangles. So that allows us to know that the two legs are congruent. And then there is a special ratio between the legs and the hypotenuse, and that special ratio is the square root of 2. Be careful to multiply or divide your radicals correctly and simplify them as necessary. And that's it, guys. That's it for 45, 45, 90-degree triangles. Thanks for watching, and I'll see you in the next video.